So, good evening students. So, we have thoroughly done Bohr's model, hydrogen spectrum, everything. But for your warming up on the spectral related calculations, today we will dedicate this complete class to solve some very familiar, very simple wavelength based, species based, energy based problems pertaining to hydrogen spectrum supported by Bohr's atomic model. So, this is only for warming up kind of an exercise. So, we will go through it. The other day I think we have discussed this flower problem. This also we have done. Now, a metal is bombarded with photons, different photons with frequencies nu A and nu B. Metal is fixed. Metal is fixed. But photons are different. One photon with nu A is the frequency, another photon nu B is the frequency. When this goes and hits the metal, electron is released with kinetic energy x. When this photon hits, another electron is released with kinetic energy 2x. And he is asking the work function of the metal. What do you mean by work function? H nu naught, the one which is absorbed here. Here also H nu naught is absorbed because the work function is a characteristic value for a given metal. So, whatever energy the incident photon may possess, the metal will always absorb a fixed part of it. The remaining energy will be converted into the kinetic energy of the electron. That we have already appreciated in the form of a graph also. The kinetic energy increases with increase in incident photon, and this being nu naught. Above nu naught, if you keep on increasing the frequency, incident frequency, the kinetic energy keeps on increasing. So, there are two different photons hitting the metal and two different kinetic energies are possessed by electrons, ejected electrons. Now, he is asking us to calculate metal's work function. So, which is a simple job. We can work out like H nu A, the first photon, is distributed like work function of the metal and also the kinetic energy of the metal, electron. In the second case, the photon has a different frequency and this will be fixed and 2x is released. Now, we need to calculate what is the value of H nu naught. So, what shall we work out? In terms of nu A and nu naught, nu A and nu B, and we do not want the x to be remaining. So, better you eliminate x. So, what for that what should we do? Just multiply this with 2, 2, 2 so that we can eliminate. Now, subtract 2h nu A minus h nu B is equal to 2h nu naught, h nu naught. H nu naught is left. I am subtracting this. So, this gets cancelled. So, H nu naught is nothing but that is what is work function of the metal. You can common H 2 nu A minus nu B. 2 nu A minus nu B. This is the I think, yeah, this is the answer. So, here what you should understand is metal's work function is fixed. If electron with greater energy impacts, the kinetic energy of the ejected electron will be more. But be careful, my dear students, if you increase the intensity with a specific frequency, more number of electrons will be released, photoelectrons will be ejected from the metal surface. Increasing intensity increases photocurrent, but increase in frequency will increase the kinetic energy. But all these things hold good if and only if the incident frequency should be more than the threshold frequency of the metal, nu naught. If the incident frequency is less than nu naught, how much ever intensity you keep, you can never eject a photoelectron from the metal surface. That you should remember. The ionization energy of helium plus is so much. Calculate the energy of first stationary state of lithium plus 2. These are very peculiar language gimmicks. Always remember one thing. Once you have an electron in the first orbit, there is an electron. What do you mean by ionization energy? Ionization potential. The minimum required potential to knock out this electron totally from the influence of the nucleus. Means what? You have to shift this electron into infinite orbital, infinite orbit, where the energy of electron becomes 0. So, indirectly what am I telling? Whatever is the energy of the electron in the first orbit, it is to be made 0. Minus 13.6 into z square to be made 0, what should I do? I have to supply plus 13.6 z square. So, the energy gap is 13.6 z square. Can't I call this as ionization potential? Can't I call this as ionization potential? Obviously, shifting electron from first orbit to infinite orbit, whatever energy is required is ionization potential. So, ionization potential of any single electron species is given by 13.6 z square electron volts, electron volt units. Be careful. Now, keep this in mind. And ionization energy of helium plus he gave this much. Calculate the energy of first stationary state of lithium plus 2. Energy of first stationary state is numerically equal to what? Ionization potential only. The energy of first stationary state in any species is numerically equal to, with sign difference, ionization potential. Therefore, what I can tell you, ionization potential of helium plus divided by ionization potential of lithium plus 2. Why helium plus? These are all applicable only for single electron species. So, is equal to 13.6 z square of z of helium plus square by 13.6 z of lithium plus 2 square, as per what I just discussed a bit earlier. Now, 13.6 get cancelled. Helium atomic number 2. So, I can say 2 square by 3 square. So, IP of helium plus is given 19.6 into 10 power minus 18 by, he is asking IP of lithium plus 2. Here what student should understand, first stationary state's energy is nothing but IP of that particular species is equal to 4 by 9. So, I want IP of lithium plus 2. IP of lithium plus 2 is 9 by 4 into 19.6 into 10 to the power of minus 18 joules atom inverse. So, if you work out this almost goes 5 times, somewhere around 45 into something. This is the answer. Very simple, the comparison of ionization energy. Calculate the shortest and longest wavelengths in H spectrum in Lyman series. He gave RH. shortest and long. See, all the transitions you must always remember in which species it is happening, in which series it is happening, and is he asking about which, the line about which he is asking. H alpha, H beta, H gamma, like a shortest wavelength, highest wavelength. These descriptions also you have to worry about or bother about. So, he is asking shortest wavelength in hydrogen spectrum. So, species is hydrogen, question is about wavelength. I told you in the beginning of this class, this particular class I am dedicating very simple problems, but this kind of habit you should have just to calculate wavelength, energy, transition, whatever. So, that is why I took one more class to solve these kind of problems. So, H spectrum, and for calculating lambda we need RH into 1 square by shortest wavelength, means highest energy. Highest energy means in the Lyman series. So, infinity to 1, highest energy. Why highest energy? Because, we want shortest wavelength. So, shortest wavelength, lambda s we will call it. So, 1 by 1 square minus 1 by infinity square, and this is going to be 0. So, lambda is equal to 1 by RH, and I told you it is 912 angstroms. This is the shortest wavelength in hydrogen spectrum. What is the longest wavelength? 1 by lambda L we will call it RH into, what is the transition for longest wavelength? Immediate next orbit to the first orbit electron should jump, means 2 to 1. So, 1 by 1 square minus 1 by 2 square, and 1 by 1 minus 1 by 4 gives me 3 by 4. So, lambda L will be 4 by 3, 1 by RH, and this is 912 angstroms, and this is going to be 304, 1216 angstroms. This is the longest, this is the shortest wavelength in hydrogen spectrum, Lyman series. Calculate the longest wavelength which can remove the electron from first Bohr orbit, given IP of hydrogen is 13.6 electron volts. What is he asking? He is asking the wavelength of a photon which can knock out the electron from the first orbit. So, you have got electron in the first orbit with what energy? Minus 13.6 electron volts energy. You want to remove this electron completely from hydrogen atom, means what? You have to take it to infinite orbit, or you should make its energy 0 with reference to this atom. So, how much energy should you supply? 13.6, because it is hydrogen atom, there is no Z square issue. So, energy required, IP is nothing but 13.6 electron volts. What is he asking? He is asking the required wavelength. So, wavelength of this transition you calculate, that is the wavelength of the photon required. So, 1 by lambda is equal to RH into 1 by 1 square minus 1 by infinity square. So, that is going to be lambda is equal to 1 by RH, 912 angstroms. So, whenever hydrogen atoms are exposed to ultraviolet light with wavelength 912 or less than 912, electron will be knocked out. That is the shortest wavelength. He is asking calculate the longest wavelength. Yeah, this is the best, or you should use lesser wavelength than this. If the wavelength increases more than this, you can't get the electron. That is it. Calculate lambda of the radiations when electron jumps from 3 to 2 in H atom. Electronic energy, actually he gave energies minus 5.42 into 10 power minus 12 joules ergs, minus 2.4 into 10 power minus 12 ergs. These are the energies of two orbits. He is asking lambda of the radiation. We want lambda. What is the lambda of the radiation? So, if electron jumps from here to here, what will happen? Some energy is lost. How much energy is lost? So, this minus this. So, 2.4 minus 2.4 minus 5.4 into, I took it common, 10 power minus 12 ergs. So, this is going to be what? Plus 3 into 10 power minus 12 ergs. And this is the energy of a photon. What is he asking? Wavelength. How to calculate wavelength? Once you know the energy in ergs, very simple. We know hc by lambda is energy only. H nu is energy. How much you got? 3 into 10 power minus 12 ergs. So, substitute these values. H is 6.63 into 10 power minus, it should not be 34, it should be 27, because we want to be in CGS, into velocity of light 3 into 10 to the power of 10 by lambda, you will get it in centimeters, is equal to 3 into 10 power minus 12. So, 3 and 3 get cancelled, 10 power minus 12, 10 power 10 become 10 power 22, this is 10 power 27. So, lambda is equal to 6.63 into 10 to the power of minus 5 centimeters. If you want to convert this into angstroms, you just divide it with 10 power minus 8, this goes up and you are going to get 6630 angstroms or somewhere like that. But my dear students, should we suffer so much to do this calculation? After all, he is mentioning everything, 3 to 2, third orbit to second orbit, electron is jumping. He wants the wavelength to be calculated. We will do it in an alternate method. We have Rydberg equation, 1 by lambda is equal to RH into, electron is jumping from 3 to 2, 1 by 2 square minus 1 by 3 square. And this is going to give me RH into 1 by 4 minus 1 by 9, LCM going to be 36, 9 minus 4 is 5. So, lambda will be 36 by 5 into 1 by RH. And what is 1 by RH? 912 angstroms. Many times I told you. And this is going to be approximately 7 times. 7 9s are 6630. Approximate. See how simply we could calculate using Rydberg equation. So, once you know the transition in the species, you can easily calculate wavelength, energy, frequency, wave number, whatever is asked, we can calculate. So, I advise students to be very much equipped with all this. That is why this warm-up exercise is going on. Calculate the energy emitted when electron 1 gram atom of hydrogen undergoes transition, giving the spectral lines of lowest energy in the visible region, its atomic spectrum. Visible region, lowest energy. In which series is formed in visible region? Which series is formed in visible region? Balmer series. So, Balmer series spreads from 3 to 2, 4 to 2, so on and so forth, infinity to 2. This is entire Balmer series. But what he wants is calculate the energy emitted when electron 1 gram atom of hydrogen. 1 gram atom of hydrogen means 1 mole. In future, we are going to do a lot of stoichiometry calculations, so many stoichiometry calculations. So, for that sake, we will see what, then we will understand what is a mole. This is called a mole. Just like you say 1 dozen is 12, 1 mole is 6.023 into 10 power 23 atoms. So, he wants lowest energy line. In this, what is the lowest energy line? This is series limiting line, highest energy. This is the least energetic line. So, we have to select that particular transition. We would like to calculate the energy of that transition, not in a single hydrogen atom, in a 1 mole of hydrogen atoms. First we will calculate per single atom, then we will multiply with Avogadro's number. So, single atom. So, we want energy this time. Energy is equal to 13.6 into 1 square, because this is hydrogen, into 1 by 2 square minus 1 by 3 square electron volts. My dear students, did you observe? If I am concerned about energy, I am taking 13.6, I am keeping electron volt there. And am I concerned with the wavelength? I will go for Rydberg equation. Here I will put RH. So, now I can calculate 13.6 into 1 by 4 minus 1 by 9, 36, 9 minus 4, 5. This many electron volts. This many electron volts. 1 electron volt is how much? 1.602 into 10 power minus, we want the answer in kilojoules. So, minus 19 joules. This many electron volts, 1 electron volt is 1.602 into 10 power minus 19 joules. I want the answer in kilojoules by 1000. I want the answer to be in kilojoules, and this is per atom. I want it per Avogadro number of atoms into 6.023 into 10 power 23. Then I would get my answer. This you can work out, so you are going to get this answer. There are 1000, 10 power minus 19, 10 power 23 is there. And I can advise you something, many times you get this. This into this will give 96.5. So this gives this into this will give 9.65, and the rest you can work out. So you are going to get this answer. See, be careful. Mole you should always multiply with Avogadro's number. Whenever you want to convert electron volt into joules, you should multiply with 1.602 into 10 power minus 19 joules. If you want to convert into ergs, 1 electron volt is 1.602 into 10 power minus 12 ergs. So, my dear students, you must be always equipped with these conversions. Coming to the next problem, it is an observation, clear thing, a theory question. Transition of electron N3 to N1 results in, electron is jumping from higher state to lower state, that too into first state, species not mentioned, we will take it as hydrogen. So, that will be ultraviolet emission, it will be an emission spectrum. Infrared no chance, band spectrum no chance, molecules give, X-ray no chance. Which of the following transitions in a hydrogen atom absorbs the photon of highest frequency? Now, absorption should take place. What do you mean by absorption? Electron must take energy. When can it happen? When electron jumps from lower state to higher state. Lower state to higher state. So, the thing is here 2 to 6 also lower to higher, 6 to 2, 1 to 2, 2 to 1. These two we can rule out because they won't absorb, they emit radiations. They give emission spectral lines, and these two will give absorption spectral lines. So, 2 to 6, 1 to 2. Which absorption takes more energy? I told you many times, the gap between 1 and 2 is too much. This gap is too much. Energy gap decreases. This is minus 13.6, this is minus 3.4, this is minus 1.51. This gap is 10.2. This gap is after all 1.9. Which gap is more? This. He is telling 2 to 6, not 2 to 3. Even then no problem. Even if you go to infinity also, what is the gap? 3.4. That is still less. 2 to infinity also 3.4. So, any transition in between 2 and infinity will be, must be less than 3.4. 2 to 1, 10.2. That is why I have been repeatedly telling the students, the energy gap between 2 and 1 is 3 times more than the energy gap between the rest of the orbits. 3.4 to 0. What is the gap? 3.4. 3.4. So, whatever transition that occurs in between will be having less energy than 3.4. So, 2 to 1 is the ultimate energy. So, now we want absorption. So, 1 to 2 is very high energy, but he wants highest frequency means 1 to 2. That is the answer. So, be careful. Which of the following transitions in a hydrogen atom emits photon of lowest frequency? Now, emission we want higher state to lower state. So, 1 to 2 ruled out, 2 to 6 ruled out, 2 to 1, 6 to 2. These two give emission. But there is one more condition. Lowest frequency should be emitted, means less energy should be emitted. Which is less energy? 6 to 2 is less energy or 2 to 1 is less energy? Generally here only students will be tempted to put 2 to 1 because the gap 2 minus 1, 6 minus 2 like, don't do like that. 6 to 2 very less energy, 2 to 1 very high energy. So, less energy transition we want, so this is the answer. One thing, otherwise that is ultraviolet light, this is visible light, because 2 to 1 is Lyman, 6 to 2 is Balmer. Paschen series, lower state should be 3, 2, 4, 5, 3. Very simple recognition. Atomic spectrum of hydrogen is explained by Bohr's theory, not Rutherford. Evidence for the existence of energy levels in atom is supplied by spectral lines. Spectral lines tell what? Discrete nature. Discrete nature is there, orbits are there, energy levels. Because of the jumping of electrons from one level to the other level, electrons emit photons. The continuum in an atomic spectrum is due to, at one stage electron lines will be very close, that instability of the excited states. The excited state electrons will quickly fall into the nearby and the energy gap between them is also very low. Which of the following electron transition hydrogen atom will require largest amount of energy? So, 1 to 2, 2 to 3, 4 to 1, 3 to 5. This is ruled out because 4 to 2 transition will release energy. 1 to 2 absorption, 2 to 3 absorption, 3 to 5 absorption. He wants largest energy. I have been telling from the beginning, 1 to 2 is a big energy gap. That is it. Any transition close to the nucleus, closest to the nucleus. Check the lower state always. The lower state is very close to the nucleus, the transition will be having more energy. The spectrum given by tungsten filament, a glowing filament. Filament is what? A spring like metal, heated, superheated metal. What is a metal? Is it a single atom? Is it a gaseous atom? Is it a molecule? It is a solid. In the beginning I told, in a solid you will have so many vibrational states, therefore you will have a continuous spectrum, close wavelengths will be released. So, you will get a continuous spectrum, but that will be emission, it is emitting radiations, almost like a black body radiation. The spectrum given by mercury or sodium vapor lamp, sodium vapor, what does it contain? It is not sodium metal, sodium vapor. Vapor always contains free atoms, Sodium metal contains associated atoms, vapor contains free atoms. Once a free atom is there, it is excited, you can say, it gives emission spectrum. Vapor means excited, so it gives an emission spectrum. Because it is atom, it will give line spectrum. Atoms gives line spectrum. We have seen sodium spectrum, I think in previous class. Atoms gives line spectrum molecules give band spectrum. So, emission and line. In hydrogen spectrum, least energetic transitions of electrons are found in which series? Least energy. Obviously, fund, because electrons jump into fourth state. Between fourth and higher states, the energy gap is very narrow. I think fund is fifth. In hydrogen spectrum, most energetic electron transitions are found in Lyman. Why in Lyman energy will be highest? Because electrons are jumping into first orbit. Let it be 2 to 1, 3 to 1. Suppose 3 to 1 means definitely 3 to 1 is more than 2 to 1. The 3 to 1 transition includes 2 to 1 energy also. This is 2 to 1, this is 3 to 1. 3 to 1 transition has more energy than 2 to 1 because some extra energy is there. That is the thing, my dear students. So, anything into 1, infinity to 1, high energy. When electrons in N shell are excited, hydrogen atom return to ground state, the number of possible lines. I think in previous class I mentioned you, if you know the limits of the orbits, first between two orbits, how many spectral lines are possible? Dear students, please don't forget the fact, this is statistical analysis. Suppose you have got hydrogen, one more hydrogen, one more hydrogen, one more hydrogen, like this. This is 2 to 1, 2 to 1, 2 to 1, 2 to 1. In all of them 2 to 1, all of them 2 to 1. I have got 10 lakhs hydrogen atoms like this. In all 10 lakhs, I am having 2 to 1 transition. What do you expect? This will release a photon, this will release a photon, this will release a photon, this will release a photon. 10 lakhs photons would come out. So, will you expect 10 lakhs spectral lines? No, because all of them have same wavelength. When all of them have same wavelength, how can you get different spectral lines? A spectral line is formed at a given wavelength. So, all of them will form a bright line, very bright line. If the repetitions increase, I told you, intensity of the spectral line will increase, but not the wavelength or frequency. A very noteworthy point, my dear students. So, take care of this. If the same, transition occurs in multiple atoms, you will get a single spectral line with a specific wavelength and frequency or wave number. Now, but this is a different case. When electrons in N shell, KLMN, ground state means K, electrons are jumping, not in a single hydrogen atom, many hydrogen atoms. Suppose it is happening in a single hydrogen atom, how will you analyze the problem? In single hydrogen atom, electron is in fourth shell, 1, 2, 3, fourth energy state. How many spectral lines are possible? We can't say. There is only one atom. So, that electron may jump stepwise. Case 1, stepwise. If it jumps stepwise, how many photons are coming? 3 photons. So, you will get 3 spectral lines because their wavelengths are not same. And you will get a Lyman line, you will get a Balmer line, you will get a Paschen line. 3 are possible. Case 1, if it happens like this. Who knows, it may happen like this otherwise. What is the otherwise? Electron may jump like this. It may first jump like this and then directly jump. So, you may get a Paschen line and then you may get a Lyman line. 2 spectral lines may be formed. This is case 2. Case 3. The electron may first jump to 2, then to 1. Here also 2 spectral lines, but a different spectrum. In this spectrum, what are you getting? You are getting a Lyman line, you are getting a Paschen line. But if the atom selects this kind of de-excitation, falling back to ground state, you may get a Balmer line and you will get a Lyman line. Here also two lines, here also two lines, but with different wavelengths. Is there any other possibility? Yes. Electron may prefer to jump directly, in which case you will get only one Lyman line. So, it's a single hydrogen atom. Anything may happen, but once you have crores and crores of atoms, all the things are assumed to be taking place, so we will count all the possible spectral lines. For that sake, yesterday I gave you one analysis. In between two orbits, how many spectral lines are possible in large number of hydrogen atoms? So, my dear students, between first and fourth, so first take the gap, 4 minus 1 is 3, we will call it x. If you want all possible spectral lines, so the formula is number of spectral lines, x into x plus 1 by 2. It is a statistically obtained easy. So, what is x3? So, 3 into 3 plus 1 by 2, 6 lines. Physically, how can you tell like this? So, 1, 2, 3, 4 and so many atoms are there. Electron may directly fall, one spectral line. Electron may fall from here, here, here to here, here to here, 3 spectral lines. So, 1 plus 3, or electron may fall directly here and then here, and this is a repetition. So, that is why you always better go like this. How many Lyman lines, how many Balmer lines? See, 3 Lyman lines are possible, 2 Balmer lines are possible, 1 Paschen line is possible. Totally how many? 3 Lyman lines, 2 Balmer lines, 1 Paschen line. So, total 6 lines are possible. There are many roads to Rome. You can calculate this in different methods. The characteristic bright line spectrum is given by, bright line spectrum is always given by excited atoms. When an electron jumps from M shell to L shell, KLMN, KLMN. Now, M to L he is asking. So, what will you get? Energy is released, emitted, very simple question. What is the difference in the wavelengths of 4th and 5th lines of Balmer series in the spectrum of hydrogen atom? That wavelength gap he is asking, 4th line and 5th line in Balmer series. So, Balmer series means what? 322 first line, 422 second line, 522 third line, 622 fourth line, 722 fifth line. First line, second line, third line, fourth line, fifth line. He is asking the difference in the wavelengths of the spectral lines. Difference in the wavelength of the spectral lines. So, you have to separately calculate the wavelengths and then work out. For a given transition, how will you calculate the wavelength? 1 by lambda is equal to, we will call it 1, RH into 1 by 2 square minus 1 by 4th 6 square. Calculate lambda 1, then lambda 2 is RH into 1 by 2 square minus 1 by 7 square. So, separately you calculate lambda 1 and lambda 2 and subtract. That will give the difference in the wavelengths. But do not calculate the energy gap and then corresponding wavelength. Go per individual wavelengths and subtract. The question is like that. If the shortest wavelength of hydrogen atom in Lyman series is lambda, longest wavelength in Balmer series of helium plus. In this problem, he changed the species, he changed the transitions also. So, compare the Rydberg equations, that is always the safest method to solve it. The shortest wavelength of H atom in Lyman series. In Lyman series, what are the transitions? 2 to 1 up to infinity to 1. And in Balmer series, 3 to 2, infinity to 2. And he wants shortest wavelength. Shortest wavelength means highest energy. Highest energy means series limiting line. So, we have to select this in hydrogen atom. And longest wavelength means less energy. Less energy means 3 to 2. H alpha line. That too in helium plus. So, we will have to write two Rydberg equations. So, first one is for this 1 by, he said anyhow this is lambda, he said it's lambda is equal to RH into 1 by 1 square minus 1 by infinity square. And for that Rydberg equation is 1 by lambda x, we will call it, we want to know this, is equal to RH into 1 by 2 square minus 1 by 3 square. And this is going to give me, if I just take a division of this, I will get lambda x by 1, RH will get cancelled. This is going to give me 1 by 1 and this will be reversed into, this is how much? 36. 36 by 9 minus 4 is 5. So, lambda x is equal to 36 lambda by 5. Is it there? Yeah. A simple comparison between two spectral lines wavelengths. Hydrogen atoms are excited to N is 4 state. In the spectrum of emitted radiation, number of lines in the ultraviolet and visible. Very simple question. See, electrons are at present in which state? 4th state. 1, 2, 3, 4. He wants how many ultraviolet lines are possible. It is not happening in a single hydrogen atom, statistical. So many hydrogen atoms are there, lakhs and crores. So, you can select all possible transitions. So, Lyman number of lines in the ultraviolet. So, it may be 4 to 1, it may be 3 to 1, it may be 2 to 1 happening in different hydrogen atoms. So, the maximum possible ultraviolet lines is 3. How many visible lines may be possible? Electron has to jump into the second orbit. It can be 4 to 2, it can be 3 to 2. So, 2 visible lines, 3 ultraviolet lines. In the diagram shows the energy levels for electrons at an atom. Which transition represents emission of a photon with most energy? See, I have been repeatedly advising the students to be worried about or bothered about the energy gaps, and he wants energy to be released. Emission. Emission means electron has to jump close to nucleus. You can't take the electron away from nucleus. So, and the energy gaps become narrow and narrow as you move away from the nucleus. So, let us observe. You can rule out this first transition because it is going up, and the second, this transition, 3 transition is good one because it is 2 to 1 ultraviolet high energy transition. And this is a visible transition, 4th one, because it is from 4 to 2. So, what is the answer? 3. This is ultraviolet, this is infrared, less. And read the question carefully, whether he is asking about wave number or wavelength, because answer will be reversed. If it is wavelength, less the energy, more the wavelength. In line spectrum of hydrogen, the third line from red end corresponds to which of the following transitions? A very trickish or silly, funny question. Third line from red end. What can you count? Red end means what? Violet to red. What is this called? Visible region. Visible region see, energy is decreasing this way, and when will you get the next thing? Highest energy of passion, which is infinity to 3, next line. So, infinity you can't do any calculations. Third line he is asking. So, in the red end third line means what? Violet end will be infinity to 2. Why? Because in the visible light, violet has highest energy. In the visible light, red has least energy. So, what is the least energy transition in Balmer series? 3 to 2. So, 3 to 2 will be the first line, 4 to 2 will be the next energetic line, 5 to 2 will be third line. This is 4 to 2, this is 5 to 2. Because as you are moving like this, energy is increasing, you are approaching towards violet. So, this kind of trickish questions you have to be careful. So, 5 to 2 is our transition. 3 to 2 is the first line in the Balmer series, 4 to 2, 5 to 2. What transition in helium plus ion shall have the same wave number as the first line in Balmer series of hydrogen atom? What transition in helium plus ion shall have the same wave number as the first line in Balmer series of hydrogen spectrum? Fantastic question. First line in Balmer series. First line in Balmer series is what? Balmer series is from 3 to 2. He is telling first line in Balmer series in hydrogen atom. So, what will be the wavelength? Sorry, wave number, nu bar 1 by lambda RH into 1 by 2 square minus 1 by 3 square. What will this be? RH into 1 by 4 minus 1 by 9, 36, 5. And this is the nu bar. And he wants the same nu bar for another transition in helium plus. So, we have to equalize. RH into 5 by 36 is equal to, this nu bar is to be repeated in helium spectrum. So, RH, because the spectrum is helium, you have to go for 2 square here into, I do not know what is the transition, N1 square minus N2 square. This I have to find. This I have to find. Now, RH and RH get cancelled and this is 4 here. So, 5 by 36 into 4 is going to be 1 by N1 square minus 1 by N2 square. See the interesting thing. He says, what transition in helium plus ion have? Yeah, he did not even mention whether the lower limit is 1 or 2 or anything. So, you have to go by trial and error, which will match to this. 36 is 6 6 are, 4 is 6 2 are 12. So, 12 square. So, you can go like that. So, work out. So, you can match N1 and N2. But a nice question. Balmer gave an equation for wavelength of a visible region of H spectrum. Lambda is equal to k n square by n square minus 4. The value of k in terms of Rydberg constant R is. Very good question. Visible spectrum. He is speaking about visible spectrum. Means definitely the lower state is fixed. Visible spectrum is always what? Balmer. In Balmer, from any higher state, electron can jump into second state. So, the transitions may be 3 to 2, 4 to 2, so on and so forth. Some n to 2, some n to 2, lower state is fixed. He says the wavelength is given by lambda some k into n square, n means this, by n square minus 4. Now, he wants the value of that k. And how to calculate lambda as per a transition is concerned? For this transition, using Rydberg equation, how will you calculate lambda? 1 by lambda is equal to RH into visible region 1 by 2 square minus 1 by n square. This we can do. So, RH into, what is the LCM here? 4n square. And what can be subtracted here? N square minus 4. N square minus 4. So, what will be lambda here now? Reverse this. 1 by RH into 4n square by n square minus 4. But he says some kn square. So, this is k, because n square by n square minus 4 he gave. So, what is k? 4 by RH. Just comparison of mathematical gimmicks. The wavelength will be minimum for which of the following electronic transition? A simple one. Minimum wavelength, maximum energy. Minimum wavelength, maximum energy. So, 624 ruled out, infrared. 422 ruled out, visible. 321, 221. Lower state is same, higher states are different. 321, 221. With both are 1, lower state is 1, then you should check the gap. 321 will definitely involve what? More energy than this. So, 321 gives a photon of highest energy. Very simple. The electron in hydrogen atom jumps from the third orbit to second orbit. The wavelength of the emitted radiation is given by, very simple, 3 to 2 transition. Go for Rydberg equation, you can easily calculate. I think this is something different. The given diagram indicates the energy levels of certain atom. These are energy levels. I think these are energies only. A photon of wavelength lambda is emitted. The wavelength of photon produced during transition from here to here, he is asking. Okay, fine. These are energy levels. I think they are energy values. Let us take them like that. So, here the energy gap is how much? E. And we want a photon of wavelength lambda is emitted when the system moves from 2E level to E level. 2E to E. From here to here. What is the energy gap? 2E minus E is E, and we know E is equal to Hc by lambda. Hc by lambda, keep it like that. Now, he wants the wavelength of photon produced during the transition from 4E by 3 to E. 4E by 3 to E, what is the energy gap? 4E by 3 minus E will be how much? 4E minus 3E by 3, E by 3. And this will have a different lambda. And we know E is equal to Hc by lambda, because he said lambda is the wavelength corresponds to E. What is the wavelength corresponds to E by 3? So, what will it be? So, let us work out E by 3. So, E by 3 is the energy now, gap is equal to Hc by some lambda x, So, what shall we do? We will divide this. So, you will get, if you divide this, you will get 3, this and this will get cancelled, lambda x is equal to 3 lambda. This is the answer, as simple as this. Or you can say one thing, when energy lambda corresponds to E energy, we want E by 3, energy is 1/3, so lambda will be 3 times more. So, this is the answer. A photon was absorbed by hydrogen atom in its ground state with electron was promoted to 5th orbit. When the excited atom returns to ground state, visible and other quanta are emitted. Other quanta emitted are. See, right now the electron is in 5th state, he says 5th orbit. 1, 2, 3, 4, 5. Already while coming back, it has already formed a visible light. He said there is a visible photon emitted and other light. So, visible means where should the electron fall? It has to fall into 2nd orbit because it should be a Balmer line. So, already electron has fallen from 5 to 2. So, what is the only photon left? 2 to 1. You just recognize visible means into 2. Nu 1 is the frequency of series limit of Lyman series. Series limit means infinite to 1. 1, 2, 3, so on and so forth, infinite. Nu 1 is the frequency. Here the frequency is nu 1 limit. Nu 2 is the frequency of first line of Lyman series. This is nu 2. Lyman series first line, and nu 3 the frequency of series limit of Balmer series. So, from here to here Balmer series limit nu 3. So, what can you say? This plus this is this. So, you can say nu 2 plus nu 3 is equal to nu 1. My dear students, be careful. Frequencies you can always add up. Do not add up lambdas, because energies can be added, frequency is directly proportional to energy. Suppose you have got h nu divided into two photons, h nu 1, h nu 2, h can get cancelled, but do not add up lambdas like that. Be careful, frequencies can be added. When transition of electron in helium plus takes place from N2 to N1, then wave number in terms of Rydberg constant. So, there is a transition taking place from N2 to N1. He said N1 plus N2 is 4, and also N2 minus N1 he said 2. From this, what can you easily make out? What can you easily make out? N2 is 3, N1 is 1, N2 is 3 and N1 is 1. So, it is 3 to 1 transition. For 3 to 1 transition, he is asking wave number. Use Rydberg equation, get the wave number. This is also just ends and things he gave. Shortest wavelength in hydrogen spectrum of Lyman series, again the same old story. Highest energy in Balmer series. So, almost wavelengths, frequencies correspond to everything. So, my dear students, we have done quite some warm up exercise today. So, now we will switch over to the wave mechanical model of atom. So, whatever we have done so far, almost with some classical Bohr's is a bit mix up. We took a light as a light as particle in Bohr's model, because photons are particles. Now, hereafter we are going to treat even electron as a wave. Light is particle, electron is a wave. We started the argument with light is a wave, electron is a particle in the beginning of the chapter. Now, we are going to take light as a particle, photons, and electron is a wave. So, in our next class, we will thoroughly appreciate how electron wave goes around the nucleus in different Bohr's orbits for a correlation, and absolute treatment of electron as a wave also we will see. From there we will switch over to quantum physics. So, have a good day, enjoy, keep solving the problems what we have sent in the form of material. Enjoy. We will meet in the next class with de Broglie.